What are the causal relationship between neurons in IT, FFA, and conscious perception of faces? IT is abbreviation of inferior temporal and IT cortex, and FFA that stands for fusiform face area. And both of these areas are a mid to late stage of visual processing in the ventral pathway. And they are likely to be responsible for conscious experience of seeing objects in the case of IT and faces in the case of FFA. And evidence includes a lesion, fMRI, electrical stimulation, and single neuron recording. So first of all, the location of the IT areas, inferior temporal lobe. So it's above V4, and it's composed of at least several areas. It's a posterior or central, and also anterior. And there is a dorsal and a ventral division between them. And in the case of the flattened brain map for the macaque brain, it's further anterior to V4. Okay, here, this 6th part corresponds to this 6th part of division of the IT. All of them are in this ventral areas, ventral surface. And this is another view of area IT. So starting from B1 and then B2, B3, B4 around here, and then further anterior, posterior, and the central and the anterior IT locates here. And these are supposed to be responding for the object vision, ventral stream. And then the question is, can we find LCC in these areas? So we first look at the damage to the ventral, what happens to these areas.
Evan suffered brain injury after being hit by a car a few years back, and that caused him to lose the capacity to recognize everyday objects. We asked Kevin what he sees when he looks at things.
I see colors, shapes, punctuated by faces, the faces of people which I really recognize, and they stand out much more than anything else. That's why I can't read words or read music anymore. So I still can imagine what it looks like in my mind's eye, but I can't imagine what it looks like, or I can't see what it looks like when I look at it. So essentially, I find things through color.
In fact, the brain needs both the structural and semantic processing to be able to interpret information transmitted through vision.
I can sometimes pick out small components of an object, and by using memory as a reference, infer what it might be. Like if something's long and silver, it could be a spoon or a fork or a knife. And usually I'll use my hands to touch the end of it. So I know, oh, it's a fork, or it's a knife, or it's a spoon. So memory does play an important role in that, and in everything I look. I mean, I come to this chair. I know it's a chair. I don't know what type of chair it is. I know it's pink, but I was able to sit down in it. But this is my house, so I know where everything is. Before I could read music, but now I can't read music anymore. So I deconstruct music in my mind's ear. So I listen to the piece and I try to separate the different instruments, what they're playing, so the bass part, the treble part, the melody, and then or any harmonies, and then I reconstruct it back for the guitar. So I'm not listening to something, the singularity is broken down. I think we do that when we learn about anything. When you're a child and you take something apart, you deconstruct it to find out how it works, and you put it back together again. And then you have this intimate knowledge about how the object works and what it is. And I do that in my mind with things that I come across, especially with music anyway, I deconstruct it. That's my son. My oldest son was Santa Claus. Yeah, Santa Claus. And this is one of my youngest son. When he was younger, he's a teenager now. Yeah, that behind that angelic face is a demon child. That's my eldest son when he was must have been about 6 weeks old, 2 months old. I think that's me. And that's Hayden, my youngest son, when he was a baby.
And do you see the details of the face? Do you see the eyes clearly? What is it in the image that you recognize?
The whole face. And I'll tell you why you can see, I can see a whole face, but I can't see a whole object. Like this thing here, I only see parts of it. Like I see these diagonal things here, but I can't see the whole thing. But with the face, I see the whole thing. So you say, well, how come I can't see that in its entirety, but yet I can see the face in its entirety? It's because a completely different center of the brain processes faces and processes objects. And in me, the part that processes objects, symbols, has been damaged, but the part that processes faces is fine. And that's how I'm able to recognize people's faces. I recognize my colleagues at work, my family. That's much, I'd much rather have the condition I have. I'm lucky because I'd rather have that than not be able to recognize faces. That would be awful. Not be able to see the people you love anymore.
Okay, so that video explained the phenomenology of the patient who had agnosia. And as the patient explained, most likely his object sensitive areas, responsible areas are impaired, while his fusiform face areas were properly intact. And that's why he was able to perceive face, but not the object, most likely. And this is the areas, the brain scan experiment, where they showed the faces and the fixation house, and then fixation and so on every 16 seconds here. Fixation, alternatingly, fixation face, fixation house, and so on. And then what they found was that this particular area of the brain, fusiform face area, responds strongly only to the face. And the other area that is next to face areas, almost, these PPA, parahippocampal press areas, they respond in only house phase, more or less, like this way. And this type of experiment is called a functional localizer. And they are the ones technique to isolate areas that respond to a particular category of the stimuli. And using this technique, people have done a lot of experiments on FFA and PPA. And coming back to the particular patient who saw the color experience upon stimulation of this color selective electrode areas here, the part that is marked by this number 178. This patient, when stimulated with the same electrodes in the same strip, but in different location here, then what they reported, especially 181 pair. Then what they said was that first of all, stimulation 177, 178. So this is the one that they reported, this left side of the box looks like a rainbow face. When I look at the face, this side looks like a rainbow undergrowing. So that's a color response elicited by color phenomenology elicited by the stimulation of this 178 electrode. But when they were stimulated with a 181, 182 pair, then he reported, your face completely changed. I don't know what's going on. Your eyes change. So when looking at the face, he feels like face is kind of distorted. And then when looking at the book cover, then just for the very first second, I saw an eye and a mouth. So that means that there is some kind of a rainbow-like thing, but about the face that is projected on this book. Okay, so stimulation of these areas do cause this kind of face-like qualia. But what's interesting is that the left side of this hemisphere, he also has a bunch of electrodes that responded to the face, which is this, represented by this red dots here. The size of the dot means that it's strongly responding selectively to the face. However, left hemisphere electrode, when they are stimulated, it only produces face-like sensation, only in a very rare cases, but not others. So the fact that there are some kind of responses there doesn't necessarily mean that when they are stimulated, it also generates a query that is related to that particular response. Okay, so it's a right hemisphere face area that seems to generate face perception. Okay, and then now that because we have the technology to do this type of fMRI experiment also in monkeys, Doris Zhao in Caltech also did combine these two technology at one time. What she found was that using fMRI, first she was able to locate very tiny response, tiny box cells in the area of the monkey's brain that is strongly responding to the face, but that's next to auditory areas and so on. And then she was also able to penetrate the brain with the electrode and then record the neurons only from that area. Okay. And then what she found was that out of more than 180 neurons that she found over that areas that responded to anything visual, then that's the y-axis of this figure. So y-axis, each of the row corresponds to different neurons, okay? And then x-axis here corresponds to the type of the stimuli. And then she presented for each of the neuron recording, she presented 96 types of the objects. And then 1 to 16 corresponds to some kind of a stimulus that is related to the face. And other images, of course, includes bodies, fruits, and gadgets, and hands, and scrambled objects, and so on. And then, as you can see, the red dot, which indicates the very strong response here, is found almost all the neurons that are recorded. And she didn't select the neurons to record. So that means that many of the neurons in that particular patch identified fMRI responded to face, and not at all to other types of the stimuli, and including something like bodies or hands that are very similar to the face in terms of biological concept, but only for the faces. So this is a quite striking finding, but 97% of the visually responsive neurons in the patch are strongly face selected, they found. Okay, so in summary, inferior temporal cortex or IT and ventral temporal cortex or FFA are crucial for object or face recognition, but they are also separate location. And the lesion of the object selective area led to the object agnosia. And if the person is lesioned in a face selective area, then it results in the face deficit called the prosopagnosia. And these patients can actually see objects. So there is a double dissociation. And also fMRI activation showed that there is a selective areas for the faces and also places or landmarks. And the electrical stimulation can cause face percept if it's done on the right hemisphere. Doris Zhao's fMRI IT recording also showed that targeted recording within the face patch identified fMRI in monkey revealed that face neurons are almost exclusively over there. So combined with the localizer fMRI, electrical stimulation, and also neural recording plus phenomenological reports from the patient, these are highly likely to be the most powerful combinations for the NCC research. But if we can do this, then can we already conclude that we are going to explain everything about the brain and the consciousness? That's a question that we are going to deal with for the next video and also for the rest of the lectures.